So in this video, I want to walk you through the system on a chip, or the SoC we will develop. We're going to call it the FPro SoC Platform, and the FPro stems from the name of the book, which is FPGA prototyping. Okay. All right, so that system, this is a full block diagram of the whole system we're going to spend the next few weeks building. And it has four major components. So the first component is actually the one at the very top in here. And what you're going to see, it actually is a processor. And that processor in here, we're going to see whatever you see in here that is gray is actually, we're going to pick up as an IP. So the majority of that block diagram in here is in white because we're going to develop it. However, we're not going to develop the processor because it's a pretty daunting task that it takes a long time. So what we're going to do is we're going to pick it off the shelf and we're going to consider it the very first part. We're not going to spend too much time on this. It's basically just setting it up. And what you're going to see is we will be using what we call a microblaze microcontroller system. So as it turns out that there are different ways or different processors that we can incorporate. We can just incorporate an ARM microcontroller or a microprocessor or any other one that, depending on which manufacturer or which company you're using or which FPGA manufacturer you're using. Since we're using Xilinx, we're going to be using the microblaze microcontroller system. Xilinx provide another version, which is a microblaze microprocessor. But we'll be doing the microcontroller system because it already has the component for the memory controller, the RAM, and everything. Within one single wizard, you can actually generate everything. Okay, so the only restriction we're going to place on that particular processor, it has to be a 32-bit processor, meaning it has a 32-bit word length and a 32-bit address space. Okay. And from there, the other restriction we're going to restrict it to is that particular microcontroller has to have a memory mapped I/O. So whenever you're actually controlling peripherals, the peripherals are seen by the processor as if they're part of their address. So they're within the same address space as the memory. You probably have seen it because most microcontrollers that you've dealt with RISC microcontrollers, they're actually this way. And by the way, Microblaze is a RISC microcontroller. And that microcontroller, you're going to see it has a bus in here, and that bus here is just an IP bus. It could be of anything, but the Microblaze it comes with an AXI bus. An AXI bus is actually pretty complicated type of bus. It actually can have distributed busing system, and there's so many signals going on. And because the purpose of this class is to show you the whole process from beginning to end of developing hardware, developing drivers, developing software and applications to control these hardware that you design. Using such IPs might be a little bit too difficult because we're gonna have to spend a few weeks just discussing how we actually use it if we want to build it from scratch on our own, not using off-the-shelf ready things. So what we're going to be doing is we're going to introduce the second part of the system. So the second part of the system is actually the bus, which we're going to call an FPro bus in here. Okay, that's thing in green. So we're going to design our own bus system, and that bus system is going to be very simple. It's not going to have an AXI. It's not going to have the fancy bells and whistles that come with the AXI bus, which comes from ARM, by the way. It's going to be basically, you're going to see it's a bunch of wires. That's what it is. And in order for us in order for the processor to actually be able to communicate and put signals on this bus, what we need some sort of a translator, and that's what the FPro bridge is for. And we're going to build this from scratch. We're going to go into details. I'm just going through an overview of the whole system. So the purpose of this FPro bus is it's actually going to understand what the AXI is putting, and then it's going to output some signals. So if the processor want to communicate with something, it will actually put it on its bus. The FPro bridge will actually translate it, then put it, and then we'll activate certain box that particular processor wants. And generally speaking, it's just putting it with the same memory address like its own internal memory. All right, so moving on to the next subsystem, you're going to see that here, or the SoC that we have we're going to develop it with two subsystems. You can have it with as many subsystems as you need, but I'm just going to introduce one that is called an MMIO subsystem, which is a memory mapped IO subsystem. And that particular subsystem in here has a bunch of slots in here that you can actually put whatever you want in it. And specifically, for the sake of consistency, we're going to have very specific number of slots, and these actually are 64 slots in here. So you're going to have from 0 to all the way to 63. You can fill all of them. You can replicate some of these if you need it, and so forth. We're probably going to utilize 10 to 12 of them. But what can you put in these slots? Well, you can actually put a timer, as you can see here, a UART. And now we can actually understand it because it's readily available to us, or we've dealt with it. A general purpose output, and you're going to see that this particular box is going to be connected to the LEDs. A general purpose input, and it's going to be connected to the slide switches, and we can control, basically you can control the LEDs and read the slide switches from here. So if you need the processor to read it, we'll be developing this particular box. We're going to go through it and connect it through the whole system. In the processor, if it needs to read the switches, all I have to do is just issue a command to read certain memory location, and that memory location happen to be connected to a certain switch, and we're going to see how we do this. But for now, all you need to know is basically you have other peripherals, whatever you've seen in a microcontroller before, you've dealt with microcontrollers before, you've seen pulse width modulation peripheral, you've seen a UART, for example, or an SPI or an I2C, you can actually put those in these boxes. And if you need more, you can actually have as many as you need. For example, in a microcontroller you've seen before, probably one of the PIC18F you've done, you've just were restricted to 2 pulse width modulation. In here, the sky's the limit. You can actually just eliminate these GPIOs and just put maybe 60 pulse width modulation, because your project has a lot of motors, or you just need it for some reason or another. It's up to you. That's the beauty of using an SoC on an FPGA, because you have the control over these. But what we're going to be doing is I'm not going to instantiate or put 60 pulse width modulation. I'm just going to show you a bunch of different IPs or peripherals, and we're going to place them in different locations in here, and how this works. So the last part of this system is actually going to be a video subsystem. And the reason why I'm introducing a different type of subsystem is the following. So the MMIO subsystem had different slots, and all of them are running in parallel. For example, the switches and the LEDs have nothing to do with each other, so the processor can communicate with both of them. Technically, the processor does not communicate with all of them at the same time, because it's still a serial one with a single core. But the idea is this port in here, and this port in here, and this port in here, and this port in here, they're all operating basically independently and simultaneously. It's just the processor talks to each one of them at the like at a very specific time, not all at the same time, but they're running in parallel, all of them. So the video subsystem is a little bit different. Its purpose is to show you a couple of things. First, which is the easiest, is actually to show you how a VGA monitor works, how to actually use the VGA port on the FPGA, and basically display things on a monitor. And as you can see in here, I have not talked about any operating system. There's no operating system. I'm just displaying outputs on a VGA completely from scratch using hardware only. The second part of the video subsystem that I want to emphasize is the following. It's actually an example of what we called a streamed pipeline data, okay, or a data stream that is pipelined through different stages. So you will have some sort of a data in here, and it will go through this particular box. It will get processed, something will happen, and then it will be outputted in here, and then it will be inputted to the second box in here, and so forth. This processes it, outputs it in here, and what you can see is this data that you generate here gets processed in this box, and all the boxes all the way to the VGA, so that you can actually display it in here. So the data is actually in a pipeline. So it's streaming, meaning it's continuous. The generation of these data points in here, well, you're going to see it's actually generated from here. But anyway, that's the first point in here that we're going to be designing. But it could be external if you choose to. Like if you connect this to an external thing, you generate data points in here continuously, and it's continuously get processed and outputs. And what you're going to see is the processor is not doing any of the processing itself. What's happening is all this data is actually being processed in the subsystem itself. So what is the processor doing? Well, the processor might actually issue certain commands. It will go through the bus, through the video controller. The video controller would know which one of these subsystems or subsystems you're trying to talk to. Let's assume that you want to talk to this particular one. So the microcontroller actually just is controlling this here, or sending it command. So this particular one we're going to see later, it's actually a mouse sprite. Its purpose is to display a mouse pointer on the screen. And what you're going to see is the displaying of the mouse pointer is not the task of this processor's task. It's actually done in here but the processor might issue some command like move it to the left or move it to the right or move it up or move it down, so you can actually see some movement of the mouse pointer across the screen. So the processor is only issuing command to move left, right, and so forth and here. And of course, you're going to see it later that we're going to actually take some sort of an input from a mouse in here through maybe a PS2 module. You're going to see that in here. A PS2 module will be connected to an external USB mouse. And then this PS2 will actually go to the processor will read it, figure out what you did with the mouse, and then will issue a different command in here, and it will actually go to the mouse and just move it. And that's the purpose of introducing a different video subsystem, because I want to show you some sort of a stream data. It doesn't have to be display data, so I can actually take this particular subsystem and replicate it and do something else with it. For example, I might do encryption or maybe compression if I choose to. And this, because we're dealing with FPGAs, this is extremely flexible. You can actually, if you see this particular subsystem, you can replicate it and you can do whatever you want with it. It's an FPGA. You're actually coding it from scratch and you're designing it. You're not restricted at all. It's not predetermined by the manufacturer. You choose.